Hello everyone, my name's Casey. Here's for my math capstone class, a friendly introduction to transfinite arithmetic and the Banach-Tarski paradox. Enjoy. So first let's start with an introduction to infinity. Despite the confusing explanations often associated with concepts of infinity, the subject isn't actually that difficult to learn, it's just kind of odd. The main issue is that infinity isn't a number, nor does it represent one, which makes it hard to do math with. What we need is a way to quantify infinity, and we do this by comparing the cardinality of groups of numbers that contain it, or sets that contain it. Cardinality is just a fancy word for the size of a set of numbers. Like our first set here, 256 has cardinality 3, as there are 3 numbers. Set 479 also has cardinality 3, so those two sets have the same cardinality. But for infinite sets, like 0, 1, 2, 3, 4, 5, 6, so on forever, is the set of whole numbers, which has a cardinality of countable infinity. And here, what we mean by countably infinite is that it's the size of a set we would create if we just started counting and kept going forever. That is countable infinity. Normally it's pretty easy to see when sets have the same cardinality, but let's try it with infinite sets. We need to make an important distinction. Two sets have the same cardinality not if they have the same number of elements, but if the elements of the two sets have one-to-one correspondence. Technically both these are true, but the same number of elements can be kind of confusing. So just like here, where 2 corresponds to 4, 5 corresponds to 7, 6 corresponds to 9 for the two sets we talked about on the previous slide. Here, every number in the first set corresponds to exactly one number in the second set, and vice versa. Now let's do something slightly off topic and mess with the set of all whole numbers. So here's a set of whole numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, yada, yada, yada. Now let's add 1 to every number. So we have 0 plus 1, 1 plus 1, and so on. And we get the set 1, 2, 3, 4, and the yada, yada. This is identical to the set of all natural numbers, or the counting numbers, just starting from 1 instead of 0. Now, does the cardinality of the set change when we add plus 1 to every element? No, it doesn't. We changed every element, but we didn't change how many of them there were. One might think that both sets are infinite, except the whole numbers also contain 0, and therefore is one number bigger. But looking at it that way, it's easy to see that the whole numbers and natural numbers are... But looking at it this way, it's easy to see that the whole numbers and natural numbers are actually the same size, as they do have one-to-one correspondence. Just change 0 to 1, 1 to 2, and you can match them up with natural numbers. The same is true with natural numbers and integers. While it's not as simple as adding plus 1 to every number, we can still match every natural number to a corresponding integer, going 1 to 0, 2 to 1, 3 to -1, 4 to 2, yada yada. So now let's move on to more of the fun stuff you can do with infinity. Say we have a circle with a diameter of 1, and therefore a circumference of pi. The diameter of 1 means it has a radius of 0.5, and since the ratio of circumference to diameter is pi, having a diameter of 1 makes the circumference pi. So let's pick a point on the circle, right here, and let's name it 1, just point 1. Now let's move one radius length, 0.5, along the circumference to get to a point 2. And we keep doing this, so we get to 3, and 4, 5, 6, 7, 8. Let's actually just, I stop here at 8, but let's just pretend we kept doing this forever. Since the ratio between radius and circumference of a circle is an irrational number, pi, we can keep doing this forever and never hit the same point twice. In fact, yeah, let's keep doing it forever. And once we're done, we can see that we've got the countably infinite set of 1, 2, 3, 4, 5, the natural numbers. Now let's remove a random individual point right here. It's just take it out of the circle and throw it away so we can never get it back. Our circle would now be incomplete. This point, we threw it away, we can't ever get it back, but we can still actually fill that point in the circle using our other points. So we could take 1 and remove point 1 and put it into the spot we removed, but now we have an empty spot here. We can move, so then we could use point 2 to fill in that empty spot that's now at point 1. Then we could use 3 to fill in the empty spot that's at point 2, and so on. We could actually keep, since we have an infinite number of points, we could actually keep doing this forever and always have another point to fill in the point we took out, which is essentially the same thing as filling in the circle. Now, the principle behind this kind of makes sense, but it also sounds kind of dumb. So let's try and phrase it in a way that sounds less dumb with Hilbert's paradox of the Grand Hotel. So here's how it works. There's an infinite number of hotel rooms and an infinite number of guests. Here, the infinite number of hotel rooms is each of these boxes, and the guest is the number inside the box. So the clerk of this hotel knows the hotel's policy is to have every room filled, and always accept every guest that comes up. A new guest comes up and asks for a room, but all of the rooms are filled. So what do? Well, he simply takes the guest from room 1, moves him to room 2, takes the guest from room 2, moves him to room 3, 3 to 4, so on, leaving an empty room for the guest to move in, and all the other guests just move to the next room. We're never going to run out of rooms to put the next person in, and we're never going to run out of people to kick out into the next room, so we can just keep doing that forever. Same thing works if someone wants to leave and you still want to have all the rooms filled. Say room number 1 left, you can move 2 to 1, 3 to 2, 4 to 3, and so on. Now, this sounds a little weird, but this is actually the same. It's the exact same logic as what we did with whole numbers and natural numbers, in which we changed the 2 to a 1, or changed the 1 to a 2, 2 to a 3, 3 to a 4, or in the whole numbers case, 0 to 1. It's the exact same thing, just put in a more commonsensical context. Anyways, so now we're going to get into the countably infinite versus uncountably infinite. Now, in this previous slide, the Hilbert's paradox of the Grand Hotel and the circles, they follow the same logic, but they're not actually the same. There's a countably infinite number of guests and a countably infinite number of rooms for the guest to fill. But in this one, we made a countably infinite number of points with this method, and we pulled in order to we could pull another thing from the sphere. Well, the entire circle is actually an uncountably infinite amount of points. But what is the difference? So countable infinity is what you get when you just start counting and never stop. But this simple definition doesn't really distinguish it from an uncountable infinity. The most important distinction between the two is that in a countably infinite set, we can pick any 2 elements, and there will be a finite number of elements between them. Or no matter what point we pick, we can always count to it. So say there's this set, the set of natural numbers, 1, 2, 3, 4, 5. How many elements are between 2 and 5? We could pick any 2 numbers on the set, but let's just pick 2 and 5. And we know there are 2 elements, 3 and 4. But we can't do this for every possible choice for an uncountably infinite set. So at what point does infinity become uncountable? At some point on this list, it turns into an uncountable infinity. It doesn't happen on the natural numbers, of course. We already covered that. Not the integers. We showed that has 1-to-1 correspondence with natural numbers. So what about the rational numbers? Well, based on what I said in the previous slide, you might think it's the rational numbers. Like if we were to write down all the rational numbers, how many numbers are between 2 and 5? Well, okay, the first number after 2 would be 2.000000 infinity more zeros down than 1, right? Well, no. This is how you should think about the real numbers, but not the rational numbers. There is actually a way we can order the rational numbers so we can tell how many numbers are between 2 and 5. To figure out why, we need to know that a rational number is defined as any number that can be created from a fraction p over q, where p and q are both integers. So we can list all the positive rational numbers as the set of the sum of sets below. Here we're just taking the set of natural numbers, right here, 1, 2, 3, 4, 5, and dividing every element by 1 to get the first set. And we take another copy of the natural numbers, but we divide every element by 2, and then do it again, but with 3, and so on. If we continue this pattern a countably infinite amount of times, we'll have every possible combination of numerator and denominator. Well, the positive ones at least, but that doesn't matter. Now all we need is a way to give this combination of sets a one-to-one correspondence with the natural numbers. So let's do that. By implementing a diagonal counting method, like in the previous slide we have 1, 2, 3, 4, 5 right here. 1, 2, 3, 4, 5. 1 over 2, 2 over 2, 3 over 2, 1 over 2. 3, it's just written differently. If we count them diagonally, we can actually order all of them into a single coherent set that has one-to-one correspondence with the set of natural numbers. And we can actually count that in the set of rational numbers in between 2 and 5. Here we go. Here we would go 1 to 2, then diagonal down, 1/2, then next row, go up diagonal this way, next column, diagonal this way, and keep counting. So between 2 and 5 there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 numbers between 2 and 5. You can actually figure that out. So that means that it means that the rational numbers are actually countably infinite. There is no number that we can pick on the scale of rational numbers that we can't count to. So that leaves us the last option of those four, the real numbers. Now, to make it a bit easier to picture, let's just think of the set of all real numbers between 0 and 1, right here. There's just a bunch of points between it, numbers between it that I can't list. So now we can think that the first number is 0, and the next number is 0.0000, infinitely more zeros than 1. The real numbers don't have a method of organizing them. There's no rules to their existence like the rational numbers, or more accurately, there's no rules but their existence. The set simply just has every number. But why does this make it uncountably infinite? Well, let's prove it. Actually, I'll continue this in the next video. I'm running out of time on the recording thing, so I'll get back to you. So we'll prove it in the next video.